You can return information to the main program by changing the values of certain arguments. That's that thing I warned you about earlier. Okay. So again, you declare the function name. It's a void. This is a symbol type. You do that before the main program. You define it inside the main program. I'm sorry, just outside. Okay. This is a little, everybody's a little bleary-eyed. You're a little tired. Are we past the point of absorbing details? Maybe there's no reason to try to go through these. So why don't we do this instead? Let's open the lecture 2.11 and look and see what the big topic is. And then the same with 12 and the same with 13. So you can go ahead and close this one. Okay, so the big topic on 2.8 was fancy output. The big topic on 2.9 are these kinds of functions, these so-called single result functions. The big topic on 2.10, these so-called void functions. And now let's see what 2.11 is. 2.11 is, the big topic is array. What's an array? There's a lot of chalk in here earlier. But somebody took the chalk in between the two classes. Okay, what is an array? An array is a collection of a whole lot of numbers or variables. Okay? What's the main advantage of an array? The main advantage of an array is that it makes writing things much simpler because you can use one name for a whole lot of things. So let me give you an example. We talked about plotting CO2 versus time. We were going to plot this function. Only the computer can't do this in closed form. All it can do is calculate the number that goes with the value at each point. So in order to create this, it uses CO2 values, maybe 100 different numbers, right, for 100 points along here. And it would have time, maybe 100 different numbers. Okay? So maybe it takes a total of 200 numbers to make this plot. 100 pairs of this value, which is CO2, and this value, which is X. 100 pairs of that. So instead of calling 100 different variables, making up names for 100 different variables, we use one name, CO2, and we give it 100 different values. So it becomes an array. Arrays can have one dimension, in which case they look like a collection of numbers that's a big long row or a big long column. All right, so let's say that our time, I'm just making this up, let's say that our time is going to go from 0 to 99 seconds. And each piece of time should be over 1 from the last one. Then the array that looks like time would look like 0, space, 1, space, 2, all the way over to 99. Or it could look like 0, 1, 2, all the way down to 0. This is an array, a one-dimensional array of numbers. This is also one-dimensional. What would a two-dimensional array of numbers look like? It could have 2 rows. It could be in this form, but have another row of numbers underneath. Or it could have 2 columns. Or it could have 100 columns. It has to be 2-dimensional. So it's arrays spread out in 2 dimensions. Three-dimensional array. What's the visual image of a three-dimensional array? It would be like a plane of numbers, that's one dimension. In front of that, another two-dimensional plane of numbers. In front of that, another two-dimensional plane of numbers. Okay? Now, three-dimensional arrays, I use them all the time. Can you imagine what I use them for? Yeah, magic. That's it. You got it. No, I use them for something else. What variable is naturally three dimensions? See? I still didn't hear you, sorry. Something that you just studied in one dimension, or maybe two, with Andy. So three dimensions is naturally any kind of position. Right? Where is my apartment located? It's at a certain dimension west, a certain dimension north, a certain dimension above sea level. Right? In the world, it takes three dimensions to say where something is. Where is that point in the corner of the room, from where I'm standing? How do I get there? I need three dimensions to get there. Go a certain amount this way, a certain amount that way, a certain amount that way. So let's say I'm a car designer, and I've taken a sculptor into my studio, and he has carved the most beautiful car in the world. Professor Moorehead, if I stand out there by the highway and I watch the cars going by, they're all different. But actually, this car is so beautiful that 2 years from now, they won't be all different. Everybody in the world is going to drive this car. That's how beautiful it is. Okay? Now, I need to put that car into a computer program. How do I do that? I choose a data point, 0, 0, 0. That's the starting point. I measure the position of every point along the curve of that car. There's three numbers, X, Y, Z. Right? That's how you get from the data to that point. And now I have a file that describes the shape of that car in three dimensions. The world is three-dimensional as far as we know in space. So I use three-dimensional numbers all the time to show position. Okay? Now let's get Professor Andy back into here. What's different about dynamics? Stuff doesn't hold still. Right? So it's not just three-dimensional. A second later, it's a different three-dimensional thing because it's moving. Stuff moves all around. So now there's four dimensions. Now I have time. So now I use a four-dimensional array to describe that car. Three dimensions to give the position, and the fourth dimension tells me time. Because the next step in time, the three-dimension position is actually different. It's not in the exact same place. It's somewhere else. So one of the dimensions is time. It measures the clock, and the other three tell me where it is in time. Okay? Only maybe that's not good enough. Maybe I want to know how fast it's going in three dimensions. So now maybe I'm up to 7 dimensions. 3 for position, 3 for velocity in 3 directions, and still time. Okay? Now that's a car. I like flying airplanes and spacecraft. The airplane not only flies around, but as it's flying around, the wings tilt this way and that way, right? That's called roll. The plane rocks forward and backwards. That's called pitch. And it also turns sideways like this. That's called yaw. Yeah, you've heard these words probably, right? I can't write anymore, sorry. So for an airplane, there's 6 dimensions. 3 positions and 3 rotations, plus time, plus velocity. So I might use a 13-dimensional array that would have in it all the information about the plane's position, the angles, the velocity of position, the angle velocities, and time. Okay? That's the idea of an array. Everybody got it? So up until this time, every variable we used, we gave it its own name. That's not practical in most engineering problems because there's so much data. You don't want to spend all day just making up names. So you can lump all the data into something that has the same physical meaning, like position, and put it in one name, or in this case time, and and then you put all those numbers in one long thing. There's 1,000 numbers in there. It's like 1,000 variables, but they all have the same name. Okay? That's an array. All right, let's look at 2.12. I have no chalk anymore. No, sorry. You know, this morning there were several pieces of long chalk, so sometime between about 10 o'clock and 1 o'clock. I have to start taking it back with me. Okay, so section 2.12 is using arrays. Now, MATLAB, the great advantage of MATLAB is that MATLAB has built in the best array handling ability of any compiler. Okay, MATLAB is terrific for doing arrays. So this is just how to use arrays, how to call a function with an array as an argument. Let's go back to that for a minute. So, you know, we keep talking about the sine function. We set up a for loop to calculate the sine so that we could change the value of y from 0 to 2 pi and calculate the value of the sine at different points between 0 and 2 pi. When you have an array variable, you could set up an array that would have all of those values in it from 0 to 2 pi, or 0 to pi over 2, I mean. And then instead of putting sine inside of a do loop that calls the sine over and over again for each value, you call sine once, with the argument being the array. And what comes back out of the sine is the array of the sines. See how beautiful that is? So if I want to know the sine of 100 different angles, instead of calling the sine 100 times with each different angle, I take the 100 angles and I put them in an array. Then I call the sine using that array as the argument. And what the sine function sends back is another array, and that array has 100 sines in it, the ones that go with those 100 numbers. How powerful is that? That's great. You want to calculate a derivative. That's something you did a lot in dynamics, I think. So if I have 3 variables, 3 position variables, I want to know the derivative so that I know what the velocity is. Instead of calling the derivative 3 times, x, y, and z, I put x, y, and z in an array, call derivative 1 time, and it comes back with derivative x, derivative y, derivative z. It's great. I want to calculate the flight of my airplane for the next 12 hours. I want to know where it is every 20 seconds for the next 12 hours. So that's 3 times per minute, 60 times per hour, that's 180, 60 minutes per hour. 180 times 12 hours is 2,160 times. I want to know where that airplane is at 2,160 points in time. I make an array with those numbers in it, 2,160 numbers. Call the position calculating program 1 time. It sends back an array, and it has the position at all those times. So this is really powerful stuff. This is where it really starts to become very, very useful for engineers. Okay, let's look at 213, the last one. So 2.13 is more on arrays, the 2B arrays. That's when you have 2 strings of numbers. There's a general piece of math which you're not going to study yet, I don't think. But if you did study this, tell me. But have you studied vectors? Yeah. Okay, there's a whole branch of math called vector calculus. And vector calculus is actually, even this is a subset. But I won't worry about the bigger one right now. I'm just going to mention there's a whole element of math called vector calculus. So from Newton and Leibniz, we figured out how to do calculus using single variables. If you have 3 dimensions, you do the problem 3 times, 1 for each dimension. At some point, mathematicians realized it would be a lot more effective if you could combine everything into a big array and then do calculus on the array. A vector, this is a 1D array. The word vector is a special word that just means a 1-dimensional array. There's a whole system of calculus called vector calculus. It's for doing 1D array. What's a 2D array called? It's got its own name. Yeah. What do you call a two-dimensional array? Maybe you've seen it written something like this. Yeah. Right, this is called a matrix. 1D array is a vector. There's a whole branch of mathematics that lets you multiply vectors, matrices, take derivatives, do the differences between them, calculate plus, minus, multiply, so on and so forth, and that is called linear algebra. Does that sound familiar? If you did the homework on the UB course, right, the UB curriculum, there's a whole course, there's a required course on linear algebra. Right? Linear algebra is how you deal with these vectors and matrices. If you get good at this, you can calculate any size problem. That's the great thing about it. And MATLAB becomes this incredibly powerful tool because MATLAB is really good at doing this kind of linear algebra, using vectors, matrices, arrays. MATLAB is really good at that. But it's only useful to you if you also are good at the math that's underneath it. You have to remember garbage in, garbage out. You have to put good input in or the computer's not going to calculate something useful. Okay, any questions? Working hard in here. Tomorrow the EAS, the other class was canceled. So as far as I'm concerned, we can meet in the morning or in the afternoon. It doesn't matter. Okay, who wants to meet in the morning? Who wants to meet in the afternoon?
What about the
Yeah, the morning wins.